Hello there. Welcome to another science lesson for today. The topic being physical and chemical changes. In our previous lesson, we reviewed the terms used, the aspects here seen in the previous topics, which are connected to the new topic, which is physical and chemical changes, where we saw that there are so many terms that were in connection to the topic we are covering now. So today, we are going to expand more, looking at the so many things that are happening around us, the reactions that are going around. There's so many changes that we always see around, but unfortunately, in one way or another, we are unable to explain or maybe to categorize them into physical and chemical changes. Just looking at the common things we encounter. Look at yourself in a bathroom, having a shower, a hot shower. After some time, what will you be seeing? You will be seeing a foggy room. That bathroom will be foggy for some time. But after you have left the bathroom, you have turned off the taps and everything in the bathroom, the fogginess will clear off. Maybe look at an old roof, roofed by iron sheets. What do you see? You see iron sheets that have undergone rusting. That's a change. Look at something like somebody passing by. How, without you seeing the person, you can easily tell who has passed. If, for example, you have interacted with that person some other time. What made you probably guess that's the person? Perfume. You got the perfume the person was wearing. How did the perfume reach you? That is a change. Look at something like timber, wood, paper burning. I'm sure you have collected some dirt. Probably it is paper, wood, timber pieces, and you burned them. What was that? That was a change. Look at something like metals being mixed. You find something like steel. You want to get steel for construction. How do they get steel? It's just a mixture of two metals. By mixing, you get steel. What is that? That's a change. Look at, for example, in your school garden, your home garden, whichever the place. You have collected so many materials, wastes, that you think it is dirt, like twigs and leaves. You throw them in a garden. After some time, a month, several months, if you go back to the garden, the leaves are no longer the way they were. What has happened? Decomposition of that material has taken place. What is that? That is a change. And so many other things, so many things that are happening around. Now, with the so many things you have seen being mentioned, and those that I haven't mentioned, but you can be thinking about them as you are seated there, can we be able to classify them as chemical or physical changes? Because I've always been saying that's a change. But which type of change? Is it physical or chemical? Now, for us to be able to classify all of those changes we have been I've mentioned, and the ones you have also mentioned in your own silent way as chemical and physical, we need to know or to define what is a chemical change and what is a physical change. So first of all, let's look at a physical change. What do we mean by a physical change? In a physical change, the two or many substances that are being involved in the change, the two or many substances that are being involved in the physical change always maintain their either one, physical properties, the physical properties of those substances will be maintained, or their chemical properties, or all. We look at the two. They will either maintain the physical properties or the chemical properties, or all the physical and chemical properties of that particular substance. It's always good to give an example. We are talking about physical change. Take an example of, you have beans mixed with the maize. You have pencils, or let me use even these mark pens of mine. I have these mark pens. These are substances. This is black, this one is blue, this is red. If I can have them separate and then put them together, these are change. Because if I'm to ask you, what is this and what is this, the answer will not be the same. This one will say, you will say that you will call it one red mark pen. But these ones, you will say it is a mixture of 3 mark pens, black, red, and blue. The fact that the name has changed, it means there's a change. But looking at this change, has the property of this red mark pen changed? Has the property of the black one changed? And has the property of the blue one changed? The answer is no. They have maintained their properties. So these properties can be in terms of physical property. Physical, it is still red. That's physical. You can see the color red, physical property. But it can also be going into what are the chemical property of this in terms of the ink is giving. Is it changing? It is still red. The chemical property that gives this ink red still maintains that chemical property of being red. But the change is there. We have a mixture of 3 and we have a single of 1. So we can see that in physical change, the components that are being involved in the change always maintain their physical, chemical, or both of the physical and the chemical properties of the same. So I was using an example of, let's say, bean seed and maize seed put together. Any kind of seed, put 2 or 3 or 4 different ones together. Will they change their shape? No. Will they change their size? No. So we are talking about physical properties. And looking at the chemical property, will that bean now change to be halfway bean and halfway maize? No. It will just still maintain the chemical properties of a bean, which is a good supply of proteins, or chemical properties of a maize, which is a good supply of carbohydrates, or a rice grain. Still, that is a seed. It will still maintain the chemical properties. So we have seen physical and chemical properties of the components are being maintained. The other property is it will maintain the state, shape, and physical composition. They maintain their state, shape, and physical composition. That second point is almost close to the first point, but here we are talking about shape. It will still maintain the shape. It will still maintain the physical composition. Physical composition. It will still maintain the state. We have the state and also the composition. Now, going back to our change, previous change of the mark pens. Look at the shape. Even if the three are combined, is the shape changed? Look at one single mark pen. The shape is still the same. So the shape hasn't changed. Look at the state. This one was in solid state. In the change, having formed the mixture, it still maintains the state, physical state. So you can see that the shape and the state never changes. Let's look at the last one, composition. Does the composition of this mark pen change? If it had a lid and the main one, and the back part, does it change? It is still the same. In the mixture, does it change? It is still the same. So you find that the second point in physical change is that the shape, the state, and the composition of the components involved is always maintained. The third point is the change can always be reversed. The change can always be reversed. However, remember that that change can only be done if there is a pathway for the change. The change can always be reversed, but remember, a pathway for the change must always be present for the change to take place. What does it mean by the change can always be reversed? Let's go back to our components. We have these three mark pens forming a change, causing a change. Three of them together is a change. Can we be able to reverse this change? We first of all have to identify the pathway of the reverse. And the pathway is, it can be, for example, maybe if they are bonded together, maybe we had some sticking components on the mark pens that when you touch the two of them together, they stick together. What will be the pathway? The pathway will be to look for a way to break the mark pens. So let's assume they were attached to each other by, let's say, glue. So how do we break it? We can break it by just pulling them apart, so that the glue that is holding the two together is broken. Once you do that, you will have gotten away with the the components that is holding the two, and that is the pathway. So first of all, you identify the pathway of breaking them. After breaking them, each one of them being on their own, you will have reversed. You have gotten your blue mark pen, your black mark pen, and the red mark pen. That is a reversed process of what you did previously of now having the three separate and putting them together. And since maybe some glue was there holding them together, you will have caused a change. But by identifying the pathway of breaking the glue, you now get the mark pens on their own. The process will have been reversed. If that happens, then that change was a physical change, because you did it using a physical process of just pulling apart the mark pens. The fourth point is that when the components are put together to cause the change, when the components are put together to form the change, no new substance is formed. That looks a bit funny. No new substance is formed. It's funny in the sense that you have two or more different components put together, but still you are saying there is no new substance is being formed after the change. Is it true? When you talk about a new substance, it means you are looking at the chemical and physical properties of the substance that has been formed. Let's look at this. Is this new substance of these three mark pens together having different properties from a single mark pen. When this mark pen is on its own, and when this mark pen is with these other two, does it have different properties? Let's look at it. If it is in this mixture, does it have this part being black and white the way it is when it's on its own? The answer is yes. Black, white. In the mixture, it still maintains black, white. These are properties. So if it can still maintain the properties it had when it is single to when it is in the mixture, then we say even this new substance that has been formed, by imagination, it is not a new substance because the properties of the components are maintained just like they were when they were in their own separate parts or points. So no new substance is therefore formed because the properties together and the properties in the single form is the same. So that point, please you note it, that even if they are together, the properties are different. They are as they were in the original state. So new substances are never formed in a physical change. Let's look at another point. Now, when you have a component, another one, they are coming together to form a mixture. This is a mixture. And we have already said in this mixture, there is no new substance formed. Do we have new bonds, chemical bonds, being broken or being formed? Are we forming any bond? Are we breaking any bond? The answer is no. This mark pen, the bond that is there to make this red, the bond that is there to make this white part, even if you place it to be in a mixture form with the others, the bond is still maintained. We haven't broken this bond. Neither are we forming a new bond between maybe this mark pen and this one. If it were that we make a new bond, it will mean we are mixing these black and red or blue and red, which will automatically give us a different color. If you will ever get colors, get blue and red, mix them. Will you still maintain blue and red? No. A new color will come by. That new color will have confirmed that there is an aspect of bond breaking and bond forming such that in the bond breaking and forming, you come up with a new different substance which will obviously be seen by the change in color. So the change in color is showing that a bond has been formed which is different, or a bond has been broken so that it can now go and bond with another one or fuse with another one to form a different substance. So in physical change, there is no bond formation and there is no bond breaking. No new bonds are formed by breaking the old ones. Lastly, in physical change, we see that the substances involved always maintain their states, though it is also very close to the second point. As I mentioned, we talked about the shape, state, and composition, but we can say that in their physical change, substances do not change their state, do not change their shape, do not change their physical composition. All these, we can summarize them into physical change does not involve change in properties. That's the main point. Under physical change, the components involved do not change in their properties. That is in summary. Properties involve all these: shape, state, composition, plus so many others include a property of a particular substance. So in physical change, properties of the components are always maintained. So when you find any change that is taking place, like the ones we mentioned of fogging in the bathroom, metals being mixed to form an alloy, and any other change you have ever seen around you, the composition of materials in the garden, just ask yourself, has a change in shape, state, composition taken place? Is a new material being formed from the old one? Are you seeing a change in terms of properties of that particular substance? If the answer is yes or no, then you will be able to categorize it into physical and chemical change. Maybe let's first of all also look at what is a chemical change. Then we will revisit those changes I mentioned plus so many others and see if that change is a physical change or a chemical change by looking at what I've just looked at in terms of physical change. And now let's look at chemical change. Now, under chemical change, after having seen physical change, chemical change has the following. Under chemical change, the following is seen. One is change in chemical composition. Change in chemical composition. You remember under physical, I asked, has the white changed? Has the black changed? And the answer was no. But when it is a chemical change, it's unfortunate that I cannot use this one as an example. But when we have a chemical change, when you have a part, a component, two components coming together, when you have these two coming together and you find that the answer you are getting is like maybe this, to separate the two, it means you have to interfere with the other one. Physically, if you are to separate these two, it means you will be interfering with the other one. So this shows that the new substance that was formed is totally different from the original components. You cannot describe this by just saying it is just red. No, it is red fused with this black. So it's totally a different substance from the components. Then, since the chemical composition has changed, therefore, of this from this, then we can say the change is a chemical change. We also gave it another name, which is a permanent change. This one is a physical change. We can also call it a temporary change. Chemical change, we can also call it a permanent change. Permanent in the sense that you cannot now change this back to this physically. You can only do it in a different way, which gives us now the second point of what is a chemical change, that it cannot be reversed. That's our second point. A chemical change cannot be reversed. And if it is to be reversed, it can only be reversed by chemical means and only if a pathway is present for you to reverse. Remember, we may have chemical changes that since we don't have any particular pathway that has been identified, you can still not be able to reverse it. But we also have some chemical changes that you can be able to reverse because a particular pathway has been identified that can be able to be used to reverse that chemical change. So, for chemical changes, there is no way you can reverse physically. Maybe let's identify an example. If you have been burning wood, so you have wood and you are burning, so you burn wood. What you will get is ash. If you look at ash and you look at wood, in terms of appearance, obviously it will be different. That comes out to be a different point, but going by the second point we are talking about, that is the chemical composition, you'll find that the chemical composition of ash and the chemical composition of wood is totally different. So being different, it shows that the change that took place, which was burning, was a chemical change. And in terms of reversing, as the first point, you cannot reverse now ash back to wood. So if the change cannot allow you to reverse, then you qualify that change to be a chemical change, just like you cannot be able to reverse ash into wood. The other change is, or the other point is, no new substance, new substance is formed. No new substance was for physical change, but when it comes to chemical change, new substance is formed. Look at an example of burning wood. Is ash the same as wood? The answer is no. So what does it tell us? A new substance has been formed. Ash is a new substance totally different from wood. So not just in terms of the chemical composition, even by just appearance, you can tell that the substance formed is totally different from the wood. Though you can go deeper and check on the chemical composition, where you will find that wood is totally different, and that is a topic for another day, where you will be looking at the chemical composition of wood. It can be seen in a branch of science called biology, where you will get that wood is made of cellulose and so many other materials. But when you look at ash, when you have burned that cellulose, you will discover that there are other components that are found in that ash. You remember when we were talking about chemical families in the periodic table, we called group 1 elements as alkali metals. Alkali metals. The name alkali coming from the word alquil, which is an Arabic name meaning ash producers. And here we are talking about ash. So ash producers. This tells us something to do with the chemical composition of ash. It is full of group 1 elements. So you find that to do with the chemical composition, ash is mainly sodium and potassium hydroxide. So it is already telling us that chemical composition is different from where it came from, and that is wood, where we have much of it that we think is the only one that is present is cellulose. When the chemical nutrients that are inside, we have sodium, potassium, and so many others that will be seen as a chemical composition of ash. So that gives us or the explanation of the second point, where we have said that new substance is always formed. Ash is different from wood. Now the other point is, in chemical change, it involves breaking and forming of new bonds. It involves breaking and forming of new bonds. To explain this part, I think I will have to take a different dimension here. I'm sure maybe in your school or at home you have gas that you use for cooking, or you have once encountered that. In school, probably we call it lab gas. This gas by name is called methane. It's called methane. By formula, methane is 1 carbon connected to 4 hydrogens. So when you have this methane gas, is also called natural gas. Natural gas is similar to what we have in biogas. Is only that we call it biogas because the composition of methane in biogas is at a smaller percentage mixed with the other gases like carbon dioxide. So because of that mixture, we call it biogas. But majorly in that biogas we have methane. Now, when we have this methane being burned, what is happening? Whatever is happening in burning of methane is this methane by this formula is combining with this oxygen, and oxygen is having that formation. Two atoms of oxygen coming together. When they burn, the products formed are carbon dioxide. We form carbon dioxide, and water. So those are the products we form: carbon dioxide and water. I want you to be keen on the connections. The connections are the bonds. These are the connections I'm talking about. These are the bonds. Are you seeing somewhere where breaking is taking place and forming taking place? Let's use red for breaking, bonds that are undergoing breaking, and blue for those bonds that have been formed. For us to form those products, which are totally different from the ones we have this side, this is water, we don't have water this side. This carbon dioxide, we don't have carbon dioxide this side. So those are totally different from now the methane and oxygen we have this side. So let's identify the bonds that are being broken with this red. We are breaking this bond, carbon and hydrogen. So this bond and this bond of carbon and hydrogen is being broken. How many are they? We have 4 of them. It is also good to know how many bonds are being broken or being formed, because as we proceed with the science, we shall reach somewhere where you will need to be able to know how much energy was involved in this process. For now, we are not going into it. We are only looking at is it a chemical change, what shows. But later on, after you have done that, you may also be asked to calculate the energy involved. So you need to know how many bonds are either being formed or being broken, so that if you are told this energy is this much, this energy is this much, can you calculate the final energy involved? You can be able. So we have carbon and hydrogen bond being broken, 4 of them. Which other bond are we breaking? We are breaking oxygen bonded to oxygen. How many are they? 1. But remember, we need always to balance the equation so that you can be able to know exactly how many have been formed or broken. Let's first of all get the balancing. Hydrogen here we have 1, 2, and here hydrogen we have 4 of them. So which means we need 2 of this water so that you can balance the hydrogens. We have 1, 2 times 2, 4. 1, 2, 3, 4. So hydrogens have balanced. Then how many oxygens do we have? Because of these 2, here we have 2 oxygen. We again have 2 oxygen on this carbon dioxide. So total oxygen is 2 plus 1, 2, total 4. How many do we have this side? 1, 2. So we need 2 at this point. So we have 2 oxygen molecules giving us 4 oxygen atoms. 2 oxygen molecules, 4 oxygen atoms. 2 oxygen atoms, 2 oxygen atoms. Total 4 oxygen atoms, balancing. So the equation has been balanced. Now from there, we can comfortably identify the number of bonds that have been broken or formed. So how many have we therefore broken here? For oxygen is now no longer 1, but we now have 2. So we have 2 for oxygen. Let's now see. We only break for the reagents. When it comes to formation, we now look for the product. So the product here, what we are having is formation. We are forming an oxygen-hydrogen bond. we have formed an oxygen and hydrogen bond. How many are they? 2 of them inside here. But remember, we have a 2 outside. So in total, how many oxygen hydrogen bonds are we having? There are not 2. There are 4. There are 4. The 4 is because of this 1 bond, 2 bonds in 1 molecule. But we are having 2 molecules, so total is 4 oxygen hydrogen bonds. The other bond is carbon oxygen. Carbon oxygen. How many are we having? We have carbon oxygen 1, carbon oxygen 2. So 2 of them. Now, has it shown that bond breaking and bond formation is taking place? The answer is yes. We have bond breaking and bond formation. That qualifies the point we have just stated, that it involves breaking and forming of bonds. If you are talking about a chemical change, it involves bond breaking and bond formation. Lastly, it involves change in chemical and physical properties. It involves change in physical and chemical properties. Let's revisit the example we have just had of combustion of methane. We revisit the example of combustion of methane. Is there a change in physical and chemical properties of the components that are involved in the process? If you look at that methane, which can also be written as this, 1 carbon, 4 hydrogens, reacting with the oxygen, which can also be written that way, giving us carbon dioxide and water as the only products. Are we seeing that aspect of change in physical, chemical, or both? The answer is yes. Unlike what we saw in physical change, under chemical change, the properties of methane are totally different from properties of carbon dioxide. Properties of methane are totally different from properties of water. Oxygen, carbon dioxide, totally different. Oxygen, water, totally different. And in fact, we may also see a case of physical state also changing. Like for this one, we have these are gas. This one is a gas. This one is a gas. And this water will also be gas in gas form. But you can also have a case whereby, for example, if you have methane gas, now let me use a more common one. If you have a reaction of water in liquid state, this water you have dropped in something that can react with it but is in solid state or can dissolve in it. So we can have our sodium chloride, or we can talk of common table salt. You remember in our last topic we talked about common table salt. What is it? And we said that is a sodium chloride, though with a combination with the magnesium chloride. So if you have this sodium chloride, it is a solid. Sodium chloride crystals, water, a liquid. When you look at the product, it will be sodium chloride but a solution. What have you done? You have changed a state. This was a solid state, and here you are talking about a liquid state. So in a chemical change, there is always change in state or change in, that's the physical states, change in the physical states of the product from the reagents or chemical properties. So physical properties and chemical properties are all involved in chemical changes. Now, this second example I've just given, where this sodium chloride is dissolving in water, you may look at it to be a physical change, because you can easily get your sodium chloride back through evaporation and crystallization. But you also have to look at it in terms of what has happened for the sodium chloride, which was solid, to go into a solution. So some of these examples will be the examples that you need to be very keen for you to be able to get the thin line between physical and chemical changes. There are those that will be showing both physical and chemical changes in one way or another. And this is an example whereby you can see there's a change, which is chemical, but you can still be able to reverse because there's a pathway you can follow to reverse this. And the pathway is evaporate to saturation. If you evaporate this solution, this sodium chloride solution, until it is saturated, leave it to cool, crystallization will take place. When you crystallize, you will get your sodium chloride crystals as a solid. Filter and you will get the crystals. You will have gotten the crystals back. That is a physical process. So on that aspect, you can take it to be a physical change. But again, when you are dissolving this solid into water, that's a chemical change, because chemical energy will be involved, something that will be discussed much later in other topics. So those are the points that we can easily follow for us to know whether a particular change is either a physical change or a chemical change. Having seen the two sets of points, I want us now to revisit back our points that I mentioned earlier, plus so many others that will be added on. Looking at the points, we categorize those changes to be either physical or chemical changes. My first statement was you are in a bathroom, having a shower, a hot shower, or can I call it a warm shower? Then all of a sudden you find that the room is misty, is foggy. What has happened? And whatever has happened, is it physical or a chemical change? Whatever happened is the fogginess or the mistiness in the room is because of the water vapor. It's because of the water vapor. We are talking about water, but is in gas form. Water vapor that was in very high concentration. A lot of water vapor is around and compressed or being limited in movement to just one particular point, and that is in that room, which is a small room. That's a bathroom. Now, because of being so much in one small area, your eye picked it to be an obstruction. Your eye picked it to be an obstruction. So you saw it to be foggy because it's an obstruction of the water in gas form. But the question is, it cleared. Why? Where did it go? In clearing, it means this water vapor that was in high concentration at one particular point where your eye picked to be an obstruction as a fog started spreading further, because remember, the room is hot. So since the room is hot, it is still injecting more heat energy into these gas particles of water by the name steam, injecting more heat energy in those particles. So as you inject in more heat energy from the room, remember your body is also hot, the particles start moving further away from each other. Start moving further away from each other. That bathroom has an opening. There is a window somewhere. So they started escaping through that window because of the high energy they are having. So as they escape, they reduce the amount or the concentration of steam, the amount of that water vapor in that room. As they reduce, your eye starts picking it as it is clearing. Obstruction is only when there is very many. But now they are reducing. So the eye will pick it to be clearing, because if they remain very few, you cannot be able to see a water molecule. It is very small. You can only manage to see them when they are in large numbers or in high concentration. It's similar to, for example, if you can get an aerial view of a person on the ground when you are high up, for example, in an helicopter. If the individual, if it is one person, you will not be able to see that one person. But assume it is a school setting. There are so many small children of even class 1 who are playing in the field outside. Even high up in the helicopter, you will easily pick out that those are people. Not really getting the shape of that person, but because there are so many, you will see those are people somewhere. Because there are so many, the eye will get it. But one person, you will not get it. So it's the same as the water vapor particle. When there are very few, the eye will not pick it. It will see it will be a clear point. But so many of them will be an obstruction and you will get it. So what was this change? The change was physical. The change was physical. Because the particles that are steam can easily be turned back to liquid by just lowering the temperature. And you easily change the liquid to vapor by increasing the temperature. So by just increasing the temperature, the water which was coming from the shower as water, having high temperature, some of the molecules broke away because of the high energy they are having, the high kinetic energy they are having, so moving away because they want to occupy another space. They have now more energy, move randomly and even faster. That was a change, a physical change, because you can still condense the steam back to liquid water. Another thing I talked about was rust. The iron sheets that are very old, they were very clear. Right now they are appearing brown in color. What has happened? Rusting took place. Is that a chemical change or a physical change? To answer that, let's look at it in terms of what is the product and what was the original. Can the product, which is the iron sheets that have undergone rust, be reversed back to the original? The answer is no, you cannot. Secondly, is the original and the present having the same chemical composition? The answer is no, because the original was just iron. But the present is, it contains an addition of water, also an addition of oxygen, also an addition of water. Water is already stated. An addition of water, oxygen, and an addition of iron itself to get our product. And the product here becomes hydrated iron oxide. Hydrated iron oxide. Are we seeing these three in this name? We have iron. We have water. The word hydrated means presence of water. And are we seeing oxygen? Yes, there is an oxygen here. So rust is just hydrated iron oxide. In particular, iron 3 oxide, because iron has 3 oxidation numbers. We have iron 2 and iron 3. Iron 3 is brown in color, iron 2 is green in color. So rust being brown, then or red-brown, depending on how you look at it, red-brown, then it's because of iron 3 oxide. All in all, what we are seeing is there is a change in chemical composition. This one is totally different from this. Physical appearance, the same, is different. This one was shiny gray. This one is red, brown. In terms of being reversible, you cannot reverse this back to this. Not unless you get a pathway, which will mean you take back the hydrated iron 3 oxide into the industry, where so many processes will take place in the industry to go back to the iron. So at least there's a pathway, but that is a chemical pathway. So this confirms rusting to be a chemical change. I also mentioned something to do with somebody passing by without your vision, but your nose assists you to identify the person passing by is this and this. So if you have ever interacted with that person, you will easily pick out the name and say it is John who is passing by, because you know he wears, or Mary is passing by, because you know she wears this particular type of perfume. So what really happened? Particles of that perfume moved from the point of source, from her, from him, to your nose. That movement is what we call diffusion. That movement is what we call diffusion. We had a high concentration of those particles around the person wearing the perfume, and less of the same around you or around your nose. So because of that, there's a movement of from high to low, diffusion. That is a physical process. That is a physical process. Physical in the sense that if you can reverse such that you have a high concentration or around you of the same perfume, and that person who was wearing the perfume does not have the perfume, the reverse will happen. The particles now will move from your point to her point, meaning that the reverse is taking place. Again, when you look at that particle of the perfume, when it moved from her to you, did it change? No. The way the scent was at her place and the way the scent was at my place is the same, meaning that there is no change in the particle. The physical and the chemical property of the components involved is the same, meaning that the change is physical. The other aspect that we looked at was look at this famous metal, which is not a metal, steel. Steel is not a metal, but we always call it a metal because we don't know. Now that we know, we should not call it a metal, but we call it an alloy. Steel is an alloy of other metals, iron being one of them. And if you look at steel and iron, if you have ever interacted with these two substances, steel as steel and iron as a metal, you find that the two are totally different in all aspects. Steel is more strong than iron. Steel can easily break. If you can inject in a lot of energy that you break it, it breaks without warning, just like glass. You bend steel, inject in a lot of energy. If it is to break, it will break without warning. But look at iron, it will bend. That's a property, totally different. Look at how much pressure the two of them can hold. Steel can hold a lot of pressure. You will have to put in a lot of energy for it to break. But iron, as much as you put in a lot of energy, it will not be as much as that of steel. Look at it in terms of rusting. If you have iron put at a place where conditions necessary for rusting are present, and in the same condition you place steel in it, steel will not rust, but iron will rust. That's a change, which is totally different. So because of those differences, where do we categorize alloying to form steel. That is a chemical change. It's a chemical change because the product and the reagents have different chemical and even physical properties, confirming that that change is a chemical change. I also mentioned an issue to do with the burning, which I've also talked about it in detail here. You are burning wood, burning paper, burning charcoal. Whatever the thing you are burning, even this plastic can be burned. This you ignite, it will continue burning until it is over. What is burning? Is it chemical change or physical change? You look at it in terms of where it is coming from and where it is going to. We saw the burning of methane, we formed carbon dioxide and water. We saw burning of wood, we formed ash. Were the products the same as reagents? The answer is no, they were different. So that confirmed burning to be a chemical change, because in all aspects of points to do with the physical change or points to do with the chemical change, it confirmed that whatever you formed was totally different from where it came from, showing that the change was a chemical change. And maybe lastly, from what I had mentioned before we add on some other things, we talked about leaves or twigs that have been thrown in a compost, in a garden or in a compost pit somewhere. After some time, a week, weeks, month, or several months, you will find that whatever you throw there is no longer maintaining the same physical appearance. Totally different. It will now be humus, being now in a form where it is in a nutrient form for even other plants to use the very nutrients. Can you reverse it back to the same leaf it was? The answer is no. So decomposition of materials in maybe a garden there, that is a chemical change, because the materials that form afterwards are totally different from the original ones, which were twigs or leaves or any material that was undergoing decomposition. So decomposition is a chemical change. Maybe to add on one or two other aspects, look at a case like making a toast. Making a toast. Probably you had one today in the morning before you came for classes. So when you are making a toast is just being made by having one piece, another piece, and there's something in between there. Put together, you have sandwiched it, or you have made a sandwich. Is it a chemical change or a physical change? That is a physical change, because that piece on this side, if I can have this, that we have these two, and we have it sandwiching this one. When they are together this way, and when they are apart, do they change their physical and chemical properties? The answer is no. This one will maintain the physical and chemical properties it has, even when it is in the toast form or in the sandwich form. So sandwiching or toasting or making a toast, that is a physical change, because there is no change in chemical properties, physical properties, there is no change, there is no new bond being formed. You are only but holding them together. In fact, your hand will be very helpful in holding them together. If you don't hold them properly, it can easily even fall off, to show that that is a physical change. Let's look at something like breaking glass. Accidentally, you are throwing a piece of stone, you hit a glass, it breaks. Is that a chemical change or a physical change? It can be a bit disturbing, because you will say broken pieces of glass are different from the whole glass the way it was. But the answer is no, they are the same. It's only that they are shattered, spread all over, but that is not a chemical change, but it is a physical change. If those pieces can be put together, they can still form glass. But one can easily say, but a bond has been broken. A bond has been broken, and therefore it qualifies to be a chemical change. The answer is yes, a bond has been broken. But can you easily reverse back the process? And the answer is yes. By just picking the pieces, melt the pieces, you take back, you form the glass piece as it was, which is a physical process. So this is one of the examples that you can easily confuse a physical and a chemical process having taken place. That shattering of the glass is indeed breaking the bond, but that breaking can easily be reversed through physical process. So that makes it to be a physical process and not a chemical process, even if it has involved shattering of glass. Maybe one last last example. For example, boiling water. When you are boiling water, is that a chemical or a physical change? When you are boiling water, you are only changing this water, which is in a liquid state, to go to water in gas state. You are only changing states, which we saw as a point in physical change. So boiling water is a physical change. However, you may find in some cases, because of breaking the bonds, because remember we said that in liquid state, the bonds are slightly stronger than the bonds in gas state. In gas state, we always sometimes tend to assume that there are no bonds between the gaseous particles. So you have broken the bonds. So does it make it to be a chemical change or a physical change? We now look at it in terms of it being either reversible or not being able to be reversed through physical state. If you look at this, it can easily be reversed by just, instead of boiling, now cool it. When you cool, a process called condensation will take place, where the gas now will move back to liquid. Since it is a physical process, then we say this change is a physical process. However, it also involved breaking of bonds or weakening of bonds. So some of the examples you will be meeting will be a bit contradicting, but always go for the aspect of it either being able to be reversed or not being able to be reversed. If it can be reversed, take it to be a physical change. And if it can't be reversed, then it will be taken to be a permanent change and not just an issue of bonds being broken or not being broken. That marks the end of our lesson today. Thank you.